All right. One more of these as a of this kind, then we'll move on to the continuous ranges. But here's a nice, neat, discrete domain to work with. Here's my function. So, and it's already solved for y. So I don't have to do any algebra first. I can just go right ahead to make my table of values and plot my points. So let's see. I put in, I'm going to use -2, -1, 0, 1, and 2. I did. So I'm going to go through down the line. I'm going to take each x, plug it in, and evaluate it. So the first one, I put in my -2. So -2 squared plus -2. Well, a negative squared is a positive. And that leaves me a final answer of 2. So my first ordered pair is -2, 2. Put my second number in, -1 squared plus the -1. -1 squared is 1, minus 1 is 0. So my second number, -1, 0, my second point. -1 squared is a positive 1. -1 by itself is -1. So 1 minus 1 is 0. And then my ordered pair is my x and my y, or my function. I'll go ahead and put 0 in. 0 squared plus 0 equals 0. Now I've got my last two. So 1 squared plus 1, which is 2. And 2 squared plus 2. So that's 4 plus 2, or 6. I'll let you guys have a second there to get caught up. Yes? Okay. Sometimes just slowing down to ask the question is enough to make you go, oh yeah, I got this. But again, all I'm doing is I'm just plugging in my x's, my domain, into the function, and I'm kicking out values for my range. Now, I also want to mention, well, this is kind of more of a sidebar, like take this guy here, 1. I'm saying f of 1 equals 1 squared plus 1, which is 2. That would be the official function notation to write that out. We'll keep exposing you guys to this function notation more and more as we progress. Now I got to graph it. So I just take my 5 ordered pairs and put them on my graph. -2, 2 is right here. -1, 0 would be here. 0, 0 is here. 1, 2 is here. And 2, 6 is here. Now the graph over this domain is this set of values that go in. They're my independent variables. Looks like that. It's a collection of 4 dots. 5 dots. Looks kind of like the Little Dipper. That's all my graph technically is. Now I have the option of adding a dotted line to show the pattern. But remember, the dotted line is not part of the graph. Officially. The dotted line is just there to show a pattern. It's not there to actually be the graph. The graph is the 5 dots. And before I leave this problem, the domain was given as -2, -1, 0, 1, and 2. It's a set, so I use the curly brackets. What's my range? What are the numbers that I get out as my dependent variables? 0, 2, and 6. 2 got used twice. 0 got used twice. Oh. Is this still a function? Because I've got -2 goes to 2, and 1 goes to 2. Is that still a function? Yeah. That's okay. Remember, if you're not sure, you can do what's called the vertical line test, which is if you can draw a vertical line and it crosses the graph 2 or more times, not a function. But if I can move this line anywhere and I only get 1 point of intersection, it's still a function. If you can draw a vertical line and it crosses the graph more than once, it's not a function. But if every time I move that line around, I only have 1 point of intersection, then it is a function. The algebraic way of thinking about it? Okay, can do that. Oh, yeah. Well. So we have domain, range, function, discrete, correct? Table of values, function notation. This is all the stuff that we need to have. Are there other questions on this one I can talk about? Okay. Put that in the can.